me who has to say thank you for all the great experience I had here. This talk sort of concludes my time in Oxford and my 2 degrees, the MSc and the DPhil. So I'm very thankful for all the great experiences and interactions, and especially to you, Chris, for supporting me during the supervision, Harvey, and Owen, of course, as well. Okay, quantum uncertainty as a fundamental limit to nature's predictability. The basic idea behind this is very, very simple. We know that quantum mechanics is a probabilistic theory, so the question arises, is it possible that future theories or alternative quantum theories could have predictive advantage by introducing new variables over the quantum theory whilst conforming to the Born rule on average? And I want to start with classical mechanics because there it's much more straightforward what's going on. So let's say we have a classical particle with position x and momentum px, and we have an apparatus with position y and momentum py. We can define a Hamiltonian, and we want to measure the property A of x px. So all properties are going to be functions of x and px, classical mechanics. And if we solve the Hamilton-Jacobi equations, then we get that in the ideal limit where we have the momentum very, very small of the apparatus, we can measure any property with arbitrary accuracy. So there's perfect measurement and no disturbance in classical mechanics. You can see here the position of the apparatus is a function of the property that is to be measured at time x0 and at time t equals 0. Okay, so here is another interaction Hamiltonian where you can measure the position and the momentum of a classical particle at the same time. We know that's not possible in quantum mechanics, but this is possible in classical mechanics. What about classical epistemic states? So if we have a subjective probability distribution over classical states, let's call it small h, then we can do a similar thing. So it's unknown what the precise details of the system are, but we can still solve Liouville's equation, and what we get is that up to the accuracy of the pointer, we can still measure the property A of x px in this epistemic way. An example for this is statistical mechanics or thermodynamics, where we just have a coarse-grained description of the system in terms of the pressure, the temperature, and the volume, for example. And let's take this example of thermodynamics. We want to measure the individual particles, and let's say that what we get is a probability distribution of velocities that looks something like the Maxwell-Boltzmann distribution. You can see there are 2 peaks. There's a reason for that will be clear in a second. So we have this coarse-grained description of this system, and when we measure, we get this distribution. So the theory here gives you state variables PTV, and we get a distribution of outcomes. So there's some uncertainty in this case. But of course, it can happen that sometimes we discover new properties of a physical system. In this case, the observer discovers that she's dealing with a gas, air. So simplified, it's made out of nitrogen and oxygen. And she realizes that actually these 2 peaks, they emerge from 2 different probability distributions that are given by whether the particle is part of nitrogen or oxygen. So what she can do is separate out 2 sub-ensembles to have what I call a predictive advantage. So you have this total ensemble that gives you the distribution here, and then you have 2 sub-ensembles that she selects out to have predictive advantage. So by the discovery of new properties, we can have predictive advantage and make the distribution finer. Maybe I can use this here. Okay. And note also that the total state is preserved on averaging. So if I neglect the information, whether the gas is nitrogen or oxygen, I get back the original distribution. So that means new variables have been discovered that are operationally accessible, condition on which I can make better predictions. Okay, what about quantum mechanics? Why do we say that quantum theory is a probabilistic theory? Here's a very simple and nice way to see why quantum theory makes probabilistic predictions. If we have a generic state of a target system and the environment, so the states of the target system are given by psi rq, and the states of the environment are given by psi prime rq. This is a general state, general density operator of the compound state. If you assume that the state of the target system is pure, what we immediately get is that the state is separable and can be written in this way. So it's just a tensor product of rho s, which is the state of the target system, and rho m, which is the state of the environment or the measurement device, let's say. And that immediately gives us a quantum decorrelation, so to say, where we have that the probabilities of x and y, where x are the outcomes of the target system and y are the outcomes of the environment, they decorrelate and can be written as a product because they factorize. And here, just apply the Born rule, and I've assumed that the measurements are represented by POVMs EX and EY for target system and the environment. So that also means that if predictive advantage exists, if these variables exist that I can introduce in an alternative theory to make better predictions, they necessarily have to be non-quantum in this way, because if they were quantum, I could write down again a state for this additional variable, and it would again have to decorrelate. So these variables will be non-quantum if they exist, and the whole program is to ask if anything, any physical principle would be violated in case they do in fact exist. And I will later try to show a result that in quantum theory, it's in fact impossible to have predictive advantage, and this rules out the existence of these variables. I do that by looking into non-locality, quantum non-locality, and I'll propose a Wigner's friend type experiment that rules it out. Wigner friend, because the measurement problem is also going to play a role here. Okay, so to summarize, the question is, if we assign a pure state to our target system, so every individual particle in that system, in that ensemble, is given by the pure state rho psi. Then the question is it possible to subselect ensembles where the distribution, the outcome distribution of the sub-ensembles is not equal to the quantum distribution? And that in turn would give us predictive advantage. Okay, just to situate the problem a bit better, as you can see, this is some sort of completeness claim, and I want to make a bit more precise what kind of completeness this is by trying to formalize and define what we mean by empirical completeness. And as you know, there are a couple of other completeness claims out there. One intuition, for example, is by Shimony, who said that a theory is complete if it says all there is to say about nature, or there's EPR completeness, where every element of reality has a counterpart in the theory. So this relates more to hidden variables, but I want to highlight that what I'm concerned here is empirical completeness. So all the variables that would give you predictive advantage are in fact accessible and operationally manipulated. And there's of course also psi antisystem. So most of the completeness claims are usually concerned with the ontic status, the quantum wave function. I focus on the empirical completeness, which asks whether the Born rule can have predictive advantage. Okay, why do I think this is interesting? So first of all, if we just take the postulates and bare bones of quantum theory, I don't think it's clear that we know all the variables that could be relevant for a measurement outcome. Quantum mechanics has the wave function, and through the Born rule, we make probabilistic predictions, but it's not clear to me that this is the end of the game, that this is the full story, and the quantum wave function is the final tool to make predictions with. And I hope it could also help to better understand quantum indeterminacy as an aspect of nature's limit to predictability, motivated by first principles. And I will show later that one of these principles is going to be non-locality. Okay, the first step for this result is I want to make some assumptions on what a prediction is going to supervene. So I'm making the assumption that all outcomes are always going to be in terms of what I call manifest configurations. This is the observational data, can be income paper or the configuration of a pointer or dots on the screen, things like that. So a prediction, everything that is directly observable, will be configurations of things in 3- or 4-dimensional space. And then there is the non-manifest domain that we use to introduce the elements and laws in our physical theories that are going to tell a story of the non-manifest domain. So this could be, for example, wave functions, or postulation that the postulate the actual particles exist. I'm mixing them up here. It's of course up for grabs if you want to distinguish the laws here from the ontological elements. What's important here is just the fact that all predictions and all the variables are going to be manifest configurations. Okay, and how do we formalize a prediction? So there is one space-like slice, for example, with a set of manifest configurations, and that is going to signify some preparation of a state, and that state is going to give us a prediction about future configurations of the manifest domain. Okay, and how does this relate to the non-manifest domain? As I just said, we have a system that might possess some non-manifest state lambda. There's an environment, there's an apparatus that is described by a non-manifest variable mu q, for example, and then the interaction of these two things are going to decide what observable is going to be measured. Okay, so sometimes it happens that we don't know the exact preparation, or we don't know what the non-manifest state of the system is, and then a prediction is the average over these states for so one preparation corresponds to probability distribution of non-manifest variables, for instance.
Is the preparation state possible in the principle?
That will be an assumption of the theory. I mean, so in quantum mechanics, of course, what we do is we are in the lab, we turn some knobs, we set up an experiment, and then the theory tells us what state we have prepared. So it's also going to be informed by the theory. And we can, of course, then test by performing measurements or doing tomography what state we prepared. So if you perform a measurement and the pointer shows a certain value, then the theory may predict that you have prepared a certain state.
Well, there's a question of which state we're talking about. There's the Y's, lambda and the lambda immediate together theory and the Y's are
Maybe we'll come back to it later. Okay, this leads me to my first definition, which is completeness and extensions on the non-manifest domain. So if two theories, T1 and T2, if for two theories, T1 and T2, the same system is described by some states lambda1, uq1, and lambda2, uq2, and it holds that at least one prediction deviates for some outcomes x, then theory T2 is said to be a metaphysical extension or metaphysical decomposition of T1 if it reproduces the same predictions on average. That's that equation. And rho of lambda2 given lambda1 is a probability distribution over the target system states of theory T2. And that depends on the details of the preparation. So it's just as before. That additional variables are added according to some new theory, upon averaging which you get the other theory back. But the new theory has a finer grained description of the system because it makes for at least some lambdas a different prediction and still gives you the overall probability distribution of the theory T1. And then a theory is metaphysically complete if it doesn't have any such extension. So for example, if we believe that quantum theory was metaphysically complete, that would mean that we couldn't introduce any hidden variables to satisfy this criterion here. But this is not a very interesting definition because for any probabilistic theory, we can always find a deterministic underpinning. By just adding enough structure and information into the initial state, you can always find a theory that is metaphysically complete and even deterministic. So it's not very interesting.
Just be clear on this one thing, the existence both of rho and GVP, is not necessarily.
Yes, so P is the probability according to theory T2, given the state lambda 2, and P here is the probability given lambda 1 according to theory T1. Yes. Okay, so this is the more important definition here where we talk about empirical extensions. If for two theories T1 and T2, the same system is described by states represented by configurations Y1 from T1 and Y2 from T2, and it holds that at least one prediction deviates, then the theory T2 is said to be an empirical extension if, again, it holds an average that reproduces the predictions of the other theory. So it's just the very same thing, but now the variables are the manifest variables that are accessible through experiment. And empirical completeness then means that there is no such extension of that theory. And the claim will be that due to quantum non-locality, there is no empirical extension or empirical extension of quantum theory. So it is in that sense complete. Okay, but there are some problems, of course. And so how do we make predictions in quantum theory? Here, the non-manifest domain consists of wave functions. So for example, we have a description psi for the target system. We have phi, ket phi for the apparatus. There is some Hamiltonian interaction between the two. And what we get is a probability. So the unitaries here, they act on the state represented by the Hamiltonian. And we assume that the measurement outcomes are represented by projection operators, Px. And so if we wedge everything together, we get the probability P of x. And usually we write it in terms of P of M's. So this is basically just the definition of the P of M. Bra psi, Ex, ket psi. This is how we make a prediction in quantum theory. But there's, of course, the measurement problem, and there are some ambiguities in what the predictions could be in all cases. So this is the macroscopic version of the measurement problem. As you well know, Wigner's friend. So we have a friend inside a box that measures some quantum system described by this superposition state. The friend has two outcomes, A and B. or 0 and 1, as you wish. And then there is a friend outside of the box that measures the joint system, which consists of system plus friend, and makes predictions about that. So now the question is, if the friend observes a definite outcome, what conclusion should we make about Wigner's probability assignments to that? So Wigner, if we believe that quantum theory holds on all levels, we'll have to say that after the interaction of the system and the friend, the whole thing must still be in a superposition. But we also assume that as soon as we perform a measurement, which is what the friend is doing, we use the reduced or polar wave functions to make subsequent predictions. So if we do that, we arrive at a contradiction because it's now not clear what story we should tell about Wigner's outcomes. Is it the case that we should use a collapse state here, or is it the case that the whole thing is still in a superposition? So if we assume that the whole thing is still in a superposition, and at the same time the friend sees a definite outcome, let's assume that's possible, then the question is, what should be the prediction of the friend for Wigner's measurements? And let's say Wigner can do two different measurements. Let's say it can be the record checking basis and the superposition basis. Intuitively we would assume that in the record checking basis, where this is one of the basis states of Wigner, it would just give you the same outcome as what the friend observed. So it's just going to the lab and asking your friend, what was your outcome? And there's a superposition basis as well that Wigner can measure in, as represented here, which is a superposition measurement on the total system consisting of friend and target system. But now it seems like that the friend has some predictive advantage. If you assume that the friend can make a prediction and the whole thing is still in superposition, then the friend can now predict with certainty what the outcome of Wigner's record checking basis measurement is going to be. Because you can just ask, and if you assume that there is consistency of the friend's outcome and Wigner, it will give the same result, but the friend also knows that the whole thing is in a superposition. So the friend seems to be in a position also to make a prediction with certainty what the outcome of that measurement is going to be. And that's weird because now we are in a situation where the friend has knowledge of two incompatible observables. Okay. So if you believe that quantum theory is valid on all scales, then it seems like the friend has some predictive advantage. And that will be important later. Okay, now second step is signal-locality and predictive advantage. Imagine a standard Bell experiment with two particles. We have a source that sends a particle to the left, one to the right. We assume that there are two observers that measure some property, let's make it spin, for example, that have two outcomes each on each side, so X and Y. And one first step to relate predictability and non-locality is if we assume that it was possible to have deterministic predictions. So assume it was possible that we can in fact have deterministic predictions. It's a very, very strong extension of quantum theory, meaning that every time we make a prediction, we know exactly what the outcome is going to be. That means that X and Y are just functions of the input settings and this additional variable set. So by the way, the set variable is the variable condition on which I have predictive advantage. So the new theory contains the variable set, and I can condition on set to give me predictive advantage. Okay. So if these are just functions, which means that the prediction is deterministic, then we can write it as a delta function, and two probabilities on both sides, they factorize. This is what this gives us outcome independence. And if we additionally assume that the two probabilities are independent of the remote setting, which is parameter independence, then we get that the two probabilities completely factorize. Okay, but we know that this is what Bell showed. It's impossible that this local description of the experiment can reproduce all of quantum theory. So if we had deterministic predictions for the Bell experiment, we would necessarily have to violate signal-locality. Okay, and here is the definition of the empirical extension. So there's some variable set for which I get a new probability that may deviate from the quantum predictions. And on average, I get back just the prediction from the Bohmian rule. Okay, that's the first step. And I want to illustrate that also in the Bohm theory, because that's very intuitive what's going on. So imagine we had a magic prediction box that gives me in each run of the experiment the initial configuration of the two particles. So in the Bohm theory, we assume that particles have definite positions, and they are guided by an additional law, the guidance equation. And what we get here is, so here I've plotted some trajectories. Since the Bohm theory is non-local, that means that whenever I change the setting here, it potentially changes the trajectory on the other side. And let's assume that the magic prediction box gives me precisely the initial condition here. Then we can plot for each initial configuration what the outcome will be. So what I've done here is, you see Q1 within the bar, that's the position of the first particle within the beam of the source, and Q2 is the position of the second particle. So we get a square of initial configurations, Q1 and Q2, and the shaded area here is the down-down output, and so on and so forth. And of course, the outcomes depend on the measurement settings. So for a maximum entangled state, we get that the number of particles that go up and down depend as the cosine squared of theta half. And theta is the measurement angle. The main point here that I'm trying to make is that you can see that if you change your measurement setting, let's say you start off with an initial configuration here, then you can choose a different measurement setting where the outcome differs. So you can choose to send information to the other party by changing the measurement setting from, let's say, here as it is now to all the way down, such that the shaded area is very small. Okay. So that's a very clear way to see how it's possible to signal in the Bohm. But however, it's important that we have access to all measurement settings. It doesn't work if we have a limited number of settings. Let's assume we only have 2 settings on each side. Then the shaded area may be maximally here and minimally here. Then you have on the top and the bottom, you have initial configurations that are not affected by the measurement settings. And with this, you can now construct a predictive advantage by saying, okay, every time I get initial configurations within this region, I just make this standard quantum prediction. And every time I get initial configurations outside, I make a deterministic prediction. So I'm saying this because it's going to be very important that we can have arbitrary numbers of measurements. Okay. And it can be explicitly constructed. So I'm not mentioning this, but if you take PR boxes as preparations of the Bell experiment here, they're empirically inequivalent to the quantum probabilities. But on averaging, for 2 measurement settings, you still get the quantum probability. So that's another way to do it. You can simulate this behavior when you have just 2 measurements each side with PR boxes. So that's a generating predictive advantage. Okay. Yeah, I will leave that. Okay. So that was the third step. And now I want to combine everything into one Wigner's friend type experiment. So we have 2 Wigners, Wigner 1 and Wigner 2. And we have the friend inside this box, just as before. And we assume that the friend has predictive advantage, which means that there exists at least one set, such that the prediction deviates from the quantum prediction. So the friend has access to a magic prediction box. And the Wigners, they can just measure in arbitrary bases, A and B, and get outcomes X and Y. And on average, the predictive advantage has to give us back the Born rule. Okay, what are the assumptions that go in here? The first one I just mentioned is predictive advantage. We recover the Born rule, but there is at least one set such that the prediction deviates. The next assumption is Signal-Locality. The Wigners cannot communicate superliminally, which means that on knowledge of set, they're independent of the remote setting. And then the third important assumption is reliable intersubjectivity, as I call it, which means that all these manifest configurations, i.e. the outcomes, X, Y, and Z, have well-defined values for all observers. They're not relative. The observers agree on X, Y, and Z. There's a single value for all these manifest configurations. And moreover, the records can be reliably reported. So if the friend observes some set here, we assume that the friend can just reliably report it to Wigner here. So you can see that might lead to problems if Wigner performs superposition measurements and messes up the memory of the friend. Okay, so that last assumption that establishes a relationship between the friend and Wigner. Okay, two more assumptions that are often implicit. No conspiracy, no superdeterminism, which means that the variable set is independent of the settings. And that was the first step. The predictions supervene on manifest configurations. So any prediction that can be possibly made is always a function of the configurations in the manifest domain. You can imagine that sometimes, I mean, in principle, it could be possible that observers have access to the non-manifest domain, where their knowledge supervenes on things that are not represented by the manifest configurations, but this assumption rules about. Okay, if we now combine the assumptions, then that is going to lead us to a contradiction, and that means that at least one assumption is gone. So what I'm doing here is some sort of Wigner friendification that combines predictability, quantum non-locality, and the measurement problem. And it's a very easy step here, and I'm stealing these ideas from Brownstein and Caves and Barrett, who formulated something called generalized or chained Bell inequalities. So why is this important? I told you before, if you have a limited number of settings, we can create predictive advantage. But now let's see what happens if we chain different Bell inequalities together, such that we have arbitrary numbers of settings. So this is a Bell inequality with n different settings. Both the Wigners and the Wigners can choose different settings here. And this is the expression of this chained Bell inequality. It reduces to the Clauser-Horner-Gimonian-Holt Bell inequality in the case of 2x2 measurements. And it turns out that for a local hidden variable theory, this whole thing must always be greater or equal to 1. But we don't want a hidden variable theory that is local. We just want to impose the assumptions that I mentioned earlier. Okay. So how does it work? We can now use IN to study the hypothetical predictions P of XY given this new variable. And it turns out that any probability distribution that satisfies my assumptions is going to give you a value that is strictly greater than 0. Okay, so this is that. And IN can be directly computed. So let's assume we have some entangled state that I parameterize by alpha. So for alpha equals 1 over square root of 2, we get the maximally entangled state. And we can rewrite IN to give us two sums here. The first one is always there. irrespective of alpha. And the second term only appears if alpha is not 1 over square root of 2, which is the case where we deal with a non-maximum entangled state. Okay. The crucial insight, and this can be called perhaps the equal probability property in Barrett and others, is that we can relate IN to the two different predictions that the friend can make from inside. So we have two outcomes. We make a prediction for the 1 outcome and make a prediction for the 0 outcome. And it turns out that the difference, so in this framework here, if I apply the equal probability property by Barrett in this framework, turns out that I can relate in this way IN and the two predictions. So you can see now already, if IN is going to be small, then the two predictions have to be equal. And when the two predictions are equal, that's exactly the quantum prediction, 1/2 probability. And that's, in fact, what we get if we impose that the theory with potential predictive advantage averages out on summing over the new variable set. Then it turns out that in the limit where the possible measurement settings goes to infinity, IN approaches 0. And that means that the probabilities have to be equal to the quantum probabilities. Okay, so where did the other assumptions go in? Most of the assumptions go in to making sense of the assignment P of X, Y given A, B, Z. So it all makes sense to talk about this probability distribution if Wigner and the friend agree on it, and it makes sense that Z is an absolute value to both the friend and Wigner. So most assumptions are implicit here, but the main one that does the work is the chain delineates. Okay, so not all assumptions can hold at the same time. A brief note on non-maximum entangled states. By the way, in order to make IN go to 0, the measurement settings we choose are projective measurements that are equally distributed around the circle. So we just have theta go from 0 to 2 pi with equal steps. And that's what makes this first term go to 0 in the limit of an infinite number of measurements. But the second term doesn't disappear. So for the non-maximum entangled state, it actually doesn't work. And what we would have to do is figure out the minimum over all different measurement settings and all different numbers of measurement settings and see what IN does in this case. But that's pretty difficult, but we don't have to do it. There is an example by Giardi and Romano where they construct a hidden variable model, which is predictively inequivalent to quantum mechanics for non-maximum entangled states. So for non-maximum entangled states, this doesn't work, only for maximum entangled states. Okay. What I find interesting now is what can we say about the predictive advantage if, let's go quickly back, if reliable intersubjectivity is violated. So I would say that signal locality and the no conspiracy assumption, no superdeterminism, and this last assumption, they appear to be a bit more natural. So if we agree that they hold, then what can we get predictive advantage by denying reliable intersubjectivity? And this is a bit speculative now, but it turns out that most interpretations of quantum mechanics don't have the property. So if you look at the Roy-Bohm theory, for example, then if you measure the friend, then the memory sometimes has to flip. So you don't get a reliable report of the outcome. In average relational quantum mechanics and cubism, you don't even have the assumption that the set variables agree for all observers. They're relative. right? So the friend may say, okay, this is my value, but there exist other branches where Wigner has a different value. Well, this is violated here. And the question would be, do we get predictive advantage here? I don't think so. So in average, for example, I think you run into problems with the self-location because the friend doesn't know which branch is going to end up in, for example. So if we deny reliable intersubjectivity, it seems like we have some sort of predictive advantage for the friend, perhaps, but there's an epistemic boundary between Wigner and the friend. Whatever predictive advantage in these theories the friend can have, it cannot be communicated to Wigner. So this is not surprising in hidden variable theory, for example, because on the non-manifest domain, on the level of the hidden variables, there can be all sorts of behavior happening, which is not accessible from the macroscopic level. And so this is an example here, but there are other examples. Okay. Now, I may run out of battery here. Yeah, let's see. I think I will make it. Okay, I want to compare. So the Wigner's friend type scenarios have received a lot of attention recently. I want to go through a couple of results here. We have, for example, Bong et al.'s result on a strong logo theorem on the Wigner's friend paradox. What they want to prove is that their assumption of absoluteness of observed events cannot hold. There's some cubist flavor in that, as you can imagine. That's the assumption they make for absoluteness of observed events. It's very similar to reliable intersubjectivity. So you have a probability distribution that all observers agree on. But on top of that, they assume that for at least or for exactly one measurement of Wigner, the knowledge of the friend is perfectly correlated. So this means in a hidden variable theory, this means that there is one single variable for one particular measurement where Wigner knows what the outcome is going to be. And they show that that's not possible. So that's a special case of what I'm proposing, because there you have a concrete theory of predictive advantage where only for one measurement you get a deterministic prediction. Right, friend? Okay, then there's also the no-go theorem on the persistent reality of Wigner's friend's perception. And this is the case where the outcomes of Wigner cannot reliably be reported to the friend. So this is the case where the memory states need to switch. And then there is Renato's and Daniela's result on quantum theory cannot consistently describe the use of itself. But here, so they use extended Wigner's friend experiments as well. But what they assume here is that the variables that the friend has access to are indeed standard quantum variables. So in fact, the correlation, the quantum decorrelation applies to the new variables that you introduce. But that obviously creates a contradiction, because if the friend uses the reduced state for subsequent predictions, and Wigner uses the superposition state, then of course they make different predictions, since the other one is effectively a collapse. But they claim that they show that quantum theory cannot consistently describe the use of itself, and that's incompatible. So the three assumptions are that quantum theory holds on all levels, there's a consistency between the friend and Wigner, and there's a single world. So that's that. And then there's one last paper here I want to mention by Kohlbeck and Renner, where they try to show that no extension of quantum theory can have improved predictive power. This is using the chain Bell inequalities, and is not intertwining it with Wigner's friend and the other assumptions that I'm making. But it's a very interesting result because they claim that they can show it for non-maximum entangled states as well. So it would be nice for the ideas that I put forward to see whether it applies here too. But there are some results, for example, by Hermans that questions whether, so there's one big assumption in the Kolbeck and Renner theorem where you have an individual system and you couple it to another system and then reduce it to the maximum entangled state. And it seems like some things go wrong because appending one system to an individual system can mess up the records, just in a way that Wigner's friend's memory can be messed up. Okay. So let me conclude, is quantum mechanics empirically complete? It seems like when we assume the assumptions that I put forward here by using the chain Bell inequalities, it's not going to be possible to find new theories with additional variables that have predictive advantage. So it's going to be impossible that we can select out sub-ensembles of a pure state that differ from the predictions of the problem. But there is an interesting twist when we look at the friend, where it seems like that when we deny reliable intersubjectivity, that some sort of internal predictive advantage is possible, but it seems like that's not as interesting as the actual predictive advantage that we would have if the selection was possible. So for example, if that existed for the friend, the internal predictive advantage, it's already for sure that it cannot be used to subselect this almost because the friend couldn't even communicate what the outcome was. So it's certainly not going to be possible to have these the subselection of ensembles. Okay, thank you.